כולם אומרים...
Think less.
יש לי טריק, כאילו, לי, זה מה שלא יכולה. למה? בשיווגה. וואי, מה זה לא הייתי צהובה שתדע?
בדוק, כן.
וואי, מה זה לא?
בדוק?
הייתי מהאלה ששוקולדית עם שיער פזור, הייתי מתעצבנת שלהם, כאילו מדהים, מה כל החרא הזה? מה זה שייך? ואפילו, תקשיב, היינו
פעם אחת, קשרנו את הכפתור פתוח
היה לנו מבחן כל שישי לפני שיצאנו הביתה, כאילו בחוץ, שאנחנו ואני טסתי במבחן של מישהו אחר, ואז המפקד כאילו במבחן קרא לי ואמר לי, זה מודיעין, זה אמינות, כאילו רצו ואני כאילו כל כך שבוע הייתי בדיכאון, כאילו סוף העולם קרה עכשיו, כאילו ממש אכל לי לקטע של אמינות, ואמר שהוא מודיעין, ובמה עמדות, הוא לא אמר כלום. באמת הסתכלת? כן, הסתכלתי, אבל זה לא בקטע שהצחקתי, אבל ניסי הצחה קלה, אני צריכה כל שבוע, זה לא כאילו הצחקתי במבחן חיי. כאילו היה לי איזה מישהו
אני לא מסתכלת אותו דבר.
סליחה שפגעתי בראש של חיובית. קיצור, אתה מבין, זה נגיד לא טוב.
לא, להפך. לא פגעת בראש של חיובי, עכשיו זה לא ראש של חיובי עליי.
לא, אבל לפחות מזה זה טוב.
כל מיני זה טוב, בדיוק.
והוא אמר לי שהוא...
אבל הוא היה מצטער שלי. הוא היה מצטער
לא, אבל בסוף הוא היה בסדר, הוא לא אמר את זה כאילו...
היא הלכה ונמצא מבחן חוזר.
afternoon. Who's taking notes today? Okay, great. Okay, so on Tuesday we discussed population coding, encoding of some variable, one-dimensional variable by a population of neurons. And we looked specifically at the case of translationally invariant dense receptive fields, where the receptive field or the firing rate as a function of the variable has the same shape for all the neurons, except that each neuron has a different preferred value of the stimulus. And we saw that in this case, if we maintain the same shape for all the neurons but just vary its width, we increase the Fisher information when we make the tuning curves more and more narrow. So it's good to have narrow receptive fields in one dimension. And what I want to do now is discuss a generalization of this to a higher dimension, but for this we also need to generalize the concept of Fisher information for higher dimensional variables. So let me start with that. Okay. So let's imagine that our variable is not one-dimensional, it's a vector. An n-dimensional vector. And in this case, it's possible to generalize the concept of Fisher information, and it generalizes to a matrix. Okay, so the elements of this matrix are given by minus the average of with respect to so the alpha beta element of the matrix, so the matrix is n by n, d to the theta alpha, d to the theta beta, probability of responses given theta. And if we want to be precise, I would write here theta prime, evaluated theta prime equals theta, and all this is averaged over the probability, the distribution of responses given theta. Okay, so in the case where n is equal 1, we have just one element in this matrix, it's a number, and you can see that this number is what we called the Fisher information before. Now remember that the Fisher information came up in two ways. One was discrimination, one was estimation. I'm going to talk about the context of estimation. So in the context of estimation, it came about through the Kramer-Rao bound. The question is, what is the generalization of the Kramer-Rao bound to n dimensions? So the Kramer-Rao bound tells us now the following. Let's first define. Okay, so the Kramer-Rao bound in one dimension related the variance of an estimator, of an unbiased estimator, to the Fisher information. So now we need to also generalize the variance, and we'll generalize it to the covariance of the estimates for the different elements of theta. So we will define E alpha beta as the average of theta alpha, the alpha element of the estimate of theta, versus the true value of theta alpha, and the same for theta beta. So this is the covariance of the estimator. What are we averaging over? No, we're not averaging over theta. Theta is fixed. Think about it also in the case of the one-dimensional. Theta was fixed. We know what is theta. We're asking if the estimator is unbiased, what will be the variance of the estimator, and why is there variance? Why is it not? Because the observations are stochastic. Okay, the observations over theta are stochastic. So this is really an average over the output of the estimator given the observations due to the fact that the observations are stochastic. Okay, so this is the estimate. This is the variance of covariance of the estimate. And now this is also a matrix. This is also an n by n matrix. And the Kramer-Rao bound tells us, I will write and then I will explain what I'm writing. It tells us that E minus J minus 1 is non-negative. Now, what do I mean? What do I mean when I write this? This is a matrix. So first of all, when I write J minus 1, I mean the inverse of the Fisher information matrix. And what do I mean when I'm writing that a matrix is larger than 0? What I mean by that is that this matrix is positive definite or semi-positive definite.
Can you repeat again what we added?
Yes. So this is the average over theta p of theta given r, p of r given the true theta. That's what it is. Right? The probability to get a certain answer from the estimator is theta is I should have no, this is just an average over p of r given theta. Yeah, because p of theta of r is deterministic. There's no reason to write this as the probability distribution. Theta given r is deterministic, and we're averaging. So imagine that there's the true theta that generates a response, and that generates an estimate. Yes.
Is the Fisher information matrix always singular, or will there be cases where we can ask inverse?
Okay, I will get to that point in a moment. So, first of all, when I'm saying that this matrix is semi-positive definite, there are several ways to define semi-positive definite. One definition is it's for if you sandwich, if you take some vector u transpose and you multiply it by the matrix A and then you multiply it by the vector u again, then whatever choice you make of the vector, you will always get a non-negative value. Semi means that it's non-negative, whereas if I would not write semi, it would mean that it's strictly positive. Okay, this is one way to define it. Now, for a matrix, if we know that the matrix can be diagonalized, this is also equivalent to saying that all the eigenvalues of the matrix are non-negative. Can this matrix be diagonalized? Can it be diagonalized? Do you know about a situation in which a matrix can always be diagonalized? If what? I just hear mumbles. I don't have an answer. What? When it's symmetric. Yes, thank you, Artur. Yes, so if it's symmetric and it doesn't have and non-singular, right? So this matrix is symmetric, right? Therefore, its inverse, if it's invertible, is also symmetric. Actually, diagonalized, it doesn't have to. It can be singular for diagonalization. So a matrix can be diagonalized. If it's symmetric, it can always be diagonalized. So this matrix is symmetric. This matrix is symmetric. The only question is the question that you asked is whether J can be inverted. Okay, so we will assume that it doesn't have eigenvalues which are 0. And you know that if J has an eigenvalue which is 0, think about the one-dimensional case. This is like saying that the Fisher information in the one-dimensional case is 0, and we know that in that case the variance is infinite. So essentially, this means that if J has an eigenvalue which is 0, then some elements of the covariance matrix must be infinite.
Why?
Because this is like taking the limit. If you would take the limit where suppose that J doesn't have an eigenvalue which is 0. Now we take the limit where this eigenvalue goes to 0, then the inverse of this matrix J, think about the one-dimensional case. I don't want to do it in detail. Think about the one-dimensional case. If J is close to 0, then everything is fine. I'm claiming, first of all, this statement is it reduces to what we said in the one-dimensional case if n is equal to 1, right? Because this is just the inverse of J is just 1 over J in that case. So suppose that J is very close to 0, everything is well defined. Now I take the variance of I take J to be approach 0. This diverges, and the variance has to diverge as well. Okay, because the variance minus something which becomes infinite is larger than 0. So I don't want to say more about that for the n-dimensional case. So let's just assume that J is invertible. So again, what the Kramer-Rao bound the theorem says is that this matrix is semi-positive definite. Now, what does that mean? In particular, if we look at the diagonal elements of this matrix, what this tells us is something about E alpha alpha. What is E alpha alpha? Where alpha is between 1 and n. What is E alpha alpha? Yes, but it's on the diagonal, but what does it mean? It's the variance of the estimate of the alpha element of theta. So based on this, now in particular, this means that E alpha alpha is larger than J minus 1 alpha alpha. And this is not because every element of a positive, semi-positive definite matrix must be positive, but the diagonal elements have to be non-negative. Okay? So for the diagonal elements, we can conclude that this is true. And so what this means is that okay, we have some bound on the variance of the estimate of the alpha element of theta, but there's one more interesting point that I want to make, and this is that you can prove mathematically, I will not do it now, that this is larger than J alpha alpha to the minus 1. And this is because J is positive definite. We haven't shown that, but that's another thing to show, that this matrix, the Fisher information matrix, is positive definite. We haven't shown it. Maybe you'll do it in an exercise.
But this is just number, right? J alpha alpha. You just said
Yes.
yes.
Yes. Yes. Yes. Yes. So this is the alpha alpha element of the matrix J to the minus 1, whereas this is taking first the element alpha alpha of J and inverting it. So mathematically, this part of the inequality that I wrote here tells us it comes up just from a property of inverses. What happens when you invert a positive definite matrix? But it also has an interpretation. This inequality has a nice interpretation in the context of estimation. So now we need to think about it a little bit. What does that mean? What is the difference conceptually between this and this? And what is the difference conceptually between the n-dimensional estimation problem, where we're trying to estimate the vector theta, versus estimating the alpha element of the vector theta? So I wonder if you can come up with what is the interpretation of this element versus the interpretation of this? Well, okay, so what I want to think about is a situation where my goal is to estimate the whole vector theta, versus a situation where my goal is to estimate only the alpha element of theta? What might be the difference between these two situations?
The value of the alpha element, if we try to maximize everything, it can be different than just maximizing.
Yes, right. So but why is there a difference?
Because they might not be orthogonal.
Okay, no. So I want to point. Yes, but I want to point to something a bit even more significant. Okay, so I could imagine trying to estimate the alpha element of theta when I tell you what are the elements of all the other thetas, all the other elements, right? And I claim that this is really the interpretation of this quantity. If you plug here alpha, this just becomes the regular one-dimensional Fisher information, right? It's just the derivative with respect to theta alpha squared, P of R. So you can interpret this as the Fisher information for theta alpha, but when you know everything else, when you know all the other elements of theta. This is, of course, an easier problem than estimating the alpha element of theta when you don't know the other elements, right? So the Kramer-Arbound, the multidimensional Kramer-Arbound tells us what is the variance of an estimator which needs to estimate all the elements of alpha. And so what this inequality in terms of an interpretation tells us is that the variance of an estimator which is trying to estimate the alpha element without knowing any of the other elements is necessarily larger, only in the case of unbiased, is necessarily larger than the variance of an estimator which knows already what are the values of the other elements. Okay? Maybe I should just point out here that what I wrote here is for the unbiased case, because I didn't say it explicitly. And you can look up, there's a generation both for the one-dimensional and multi-dimensional case of the Kramer-Arbound for the case where estimators are biased, but I don't want to go into it.
Why is there -1 when you don't know the other?
Well, because this is just the Kramer-Arbound tells us something about an estimator which has to estimate all the elements of theta. So the reason I'm saying this is saying something about that situation is because of the Kramer-Arbound. The Kramer-Arbound tells us that the variance of the estimator in this case will be bounded by this quantity, and this is an estimator whose task is to estimate concurrently all the elements of theta. Right? Okay. Whereas this one, mathematically, you'll just see that once you write, the Fisher information here becomes the derivative with respect to theta alpha squared of P of R given theta for a particular value of theta. So this is like when you know all the other elements of theta. Okay, it's a bit subtle. You should, if it's not clear right now, you should think about it more carefully after the class. All right, now once we've done that and discussed Fisher information in multi-dimensions, I want to go back to the question of wide versus narrow tuning curves. So, for example, you can think of place cells, which represent position in a two-dimensional space, or maybe in three-dimensional space. In bats, there are place cells which represent three-dimensional space. So you have neurons whose receptive field is some blob around a particular position, and roughly speaking, all the different neurons have similar receptive fields, but with different preferred locations. So let's rethink about the question of translationally invariant receptive fields, dense receptive fields. So for example, in 2 dimensions, I can imagine that I have a box, a square of dimensions L by L, and the receptive field of a particular neuron might be, the neuron might be active in some in particular area, and another neuron, then you will have other neurons with exactly the same structure of receptive field tiling the whole plane. And if it's d-dimensional, then it's a d-dimensional box. So what can we say about what has changed from the one-dimensional case? One thing that's changed is the relationship between L and the number of neurons. So we know that the neurons need to tile the whole d-dimensional box. And so if I would call the distance between the centers of receptive field of neighboring neurons delta theta, what we have now is that L divided by delta theta to the power d is equal to n. Okay? So delta theta to the power d is equal to L to the d divided by n. And you will see that this will make a difference in our argumentation. And so this is related to what I told you at the end of the lecture on Tuesday, that the way that the number of neurons scales when you change, the way that the number of neurons scales with the dimensions is different in the d-dimensional case compared to the one-dimensional case. All right, so let's think about every element of the Fisher information matrix. Okay, we need to do a few steps that I think I will skip some of them. But remember that when we wrote the Fisher information in one dimension, we summed over the contributions of all the neurons, and this sum, we replaced it by an integral, right? We were able to do this because the receptive fields of all the neurons have the same structure but translated. So summing over all the neurons becomes like an integration over the difference between the theta that we're trying to estimate and the center of the receptive field of each neuron. So we can do the same thing in d dimensions. But one thing that will change is this. So remember that we had a sum over all the neurons, and to turn it into an integral, we divided by 1 over delta theta and multiplied by delta theta. And then once you have a sum, delta theta times something where you change theta, this is like an integral. And in d dimensions, we need inside the integral delta theta to the power d, right? Because in each one of the dimensions of the integration, you need a delta theta, right? So in the one-dimensional theta, one-dimensional case, we had delta theta sum over theta I, and that became an integral. And now in the multidimensional case, we need something like delta theta to the power d sum over theta I to write the sum as an integral. So this means that we'll have a prefactor here when we take the limit where the neurons are dense, and we want to express things in terms of an integral. We'll have a prefactor which, instead of being 1 over delta theta, it will be 1 over delta theta to the power d. So this will be n divided by L to the d. And then, so maybe I will just write here 3 dots to clarify that I didn't do all the steps in detail, and you can complete them. So we'll have an integral t to the d theta d alpha, something that looks like d alpha f d beta f divided by f. Okay. Now we can ask what happens if we write the receptive field. F is the receptive field, what if you write the receptive, and maybe I should write here large f because to be consistent with what I did on Tuesday. And if we say now that f is some function, so f of theta is some function of theta divided by some parameter s, and we do the same thing that we did last time. So here, nothing, when we plug f, the derivative of f, here we get a factor of 1 over s squared, which we got also last time for the one-dimensional case. But here we have f entering in the when we change the variables, when we write x hat is equal to theta hat over s. When we do the change of variables, we get s to the power d. So eventually, when we plug this here, we write this in terms of this integral in terms of x. We will get that j alpha beta scales like s to the power d minus 2. Again, in the one-dimensional case, d was 1, and what we got is that we had j scaling like 1 over s. And now it's d minus 2.
Why
The minus 2 comes from these derivatives, and the d comes from the change of variables here. Okay, but now this is quite remarkable. What you see is that in one dimension, we have 1 over s. So in 1D, I'll continue over there. In 1D, j is proportional to 1 over s. So narrow turning curves are better. The narrow turning curves give us higher Fisher information. In 3D, or in D larger, okay, let's do 3D. J is proportional to S. So now wide tuning curves are better. And this will be true for any D larger than 3, actually larger than 2. And quite remarkably, in 2 dimensions, just J is independent of S. So in 2 dimensions, if you set up a set of neurons that have, say, Gaussian receptive fields in 2 dimensions, and you just put the centers of receptive fields in different positions, tile the plane, then overall your ability to estimate a variable based on their joint activity will be independent of the width of these Gaussians. Okay? And the whole thing has to do with 2 opposing effects, as we discussed last time. When we change the width of the receptive fields, we make the single neurons that respond, if we make it, say, more narrow, we make the single neurons, some of the single neurons that respond, more sensitive, that their activity depends more strongly on the variable, so they provide more Fisher information, but the number of neurons that are actually responsive goes down. And the balance between these two effects is what is determining whether it's better to have wide or narrow receptive fields. So in 1 dimension, what wins is the fact that the neurons becomes more responsive. In 3 dimensions, what wins is the fact that you have more neurons that are responding. And in 2 dimensions, just the 2 effects are balancing each other. Now, I should mention also that all this is under certain limits. We have to be in the limit where we have dense receptive fields and where the range of the representation is large compared to the receptive field of each neuron. So for example, in the 3-dimensional case, the argumentation has told us that we want to make the receptive fields as wide as possible, but this is not really true. When will we stop? we will not increase the width of the receptive field indefinitely.
Gaussian ending too large in the situation that we need to increase.
Yeah, so we will stop when the width of the receptive field is already comparable to the size of the box. It's quite clear if you will take the limit where the width of all these receptive fields is much larger than the box, then all the neurons are just, then the whole argumentation will not work because we're not getting the additional information from additional neurons outside the box that are implicitly present in this calculation. In this calculation, we increase the limits of the integral from -infinity to infinity. Okay, so and then there's another thing to keep in mind, which is true for any use of Fisher information to estimate, to ask something about the ability to do a fine estimation or fine discrimination, and this is that the Kramer of fine estimation, so that the Kramer-Rao bound is a bound. It becomes saturated under certain conditions. When you have sufficiently large amount of independent observations, then the Kramer-Rao bound really tells us what is the variance of an estimator. So in the context of neurons, this can come about in two ways. One is that when we're adding more and more neurons, we're making them more and more dense, eventually the Kramer-Rao bound will always be saturated. And the other one is that if you just increase the firing rate of all the neurons. You can think that these are Poisson neurons, so a large firing rate, you can think about it as a sum of independent observations with smaller firing rates. That's also a situation where Kramer-Rao bound is saturated. But there are situations, for example, if you try to estimate the Fisher information of a small number of neurons with low firing rate, it might not tell you correctly what is the estimate of an optimal estimator. There are some nice works on this. I can maybe put some references on the Moodle. You have to remember that in some situations the Fisher information itself is not a good way to estimate the variance of an estimator.
Assume the high firing rate in what we did?
I did not. So that's why I'm saying all this. What we did is precise for the Fisher information, but whether or not the Fisher information tells us something about an estimator also includes in it some limits. Okay, the limit where you have a large number of neurons or high enough firing rates. One last comment on this is that when we varied the width of the receptive field, we did something. We made a choice. We made it. What are we keeping fixed in this choice? While we're taking a certain structure of the receptive field, and we're varying it. We're varying the width. What are we keeping fixed? The number of neurons. But what for the receptive field?
It decreases in the same way in all dimensions.
Okay, so that's everything you're saying is correct, but not what I want to discuss. So we have, this is firing rate, or the capital F was the firing rate multiplied by the time of observation, and this is, say, theta, and we're looking at something like this versus something like this, right? What have we kept fixed? The maximal firing rate, right? Now, so you can note that when we make the tuning curve wider, we're going to end up with more spikes from the whole population. So we're not maintaining a fixed number of spikes from all the population of neurons. We could have done the same exercise while saying what we want to keep fixed is not the maximal firing rate of each neuron. What we want to keep fixed is the total number of spikes, the firing rate from the whole population. Maybe there's a constraint. The important thing is that there's some metabolic constraint on a spike, and when biology needs to decide on whether to choose a wide or narrow receptive field, the important constraint is the total number of spikes that are generated with the population. Well, because just by definition, when I write that f is g of theta divided by s, that's the way it happens, right? When I change s, I change the tuning curve in this way. I could have decided to, when I vary s, also to scale g, such that in this case I will have a lower maximum firing rate such that the total number of spikes will remain fixed. If you would do that exercise, you would find that narrow tuning curves are always better. Okay? So this also is related to a fundamental difficulty when we discuss optimization arguments in biology, and this is often we don't know what is the constraint. We often don't. We hypothesize that biological system is trying to optimize something. Maybe we're wrong about that as well, but also we don't. It's very important to ask what are the constraints. Now we do know that I think that the constraint on the maximal firing rate makes sense in the sense that we know that at least in particular areas of the brain, in the cortex, in retina, there is a typical maximal firing rate that neurons can fire, but it's not obvious why. Yes.
Do you see in biology that there are differences in the size of receptor field? I mean, like if you compare the size of, let's say, cell segmentation in mouse to bats, that size really?
Yeah. So this is an interesting question. First of all, in 2 dimensions, so in mice, most of the research on place cells was done in mice. And at least this argument tells you that the width of the receptor field is not even important in 2 dimensions. Now in mice, there is a certain width, and actually there's not just one width. There is a certain gradient of width along a certain axis in the hippocampus. So I don't expect that this theory is telling us everything. Now, but if you believe this theory, you would think maybe in bats, the receptive field should be huge. Not so clear. Not so clear. I think what would be an important experiment would be to do this in different environments of different sizes, because as we discussed, it's not really true that you can make the receptive field as large as you want. At a certain point, when it becomes comparable to the size of the environment, it's not beneficial to increase it more. So if we just make the hypothesis that the width of receptive field, say in bats, is set by these arguments, which might not be the case, but even if we believe that, our really prediction is that the receptive field should scale with the size of the environment. So I'm not sure. I don't think that this experiment. In mice, it's more subtle. I'm not sure. For example, for grid cells, which are also representing position, it does not scale with the environment. But yeah. So anyway, in bats, I don't think that the experiment has been. Now it's being performed maybe in Nachum Molodomsky's lab in the Weizmann Institute. But the original experiments were done in a particular size of room.
But also the assumptions are quite not biological level, right?
Which one?
The depth and the translation and the environment.
No, but this is really more or less what you see. You see in the hippocampus a representation of all possible positions, and all the cells have similar, at least in environments that are not huge, all the cells have unimodal receptive fields which have a similar structure. So it's not so far from biological reality. And there are many examples in the brain for this translational invariant dense receptive field. For example, orientation tuning. So you have neurons responding to every possible orientation with similar receptive field. There are many other examples.
And I had another question again about the consequences of this constant maximal.
Yes.
You said something about the consequences.
Well, I just said that if that would not be that was what we assumed in the calculation.
Yeah.
If instead we would assume that as we're varying the width of the receptive field, we're also varying the maximum such that the total rate of spikes on the whole population is fixed, then things would change. Let's see. Maybe I will just tell you what we will do in the next lecture, which will be on Thursday, because next week on Tuesday it's ISFN. So I will just describe very briefly what we will do. what I want to discuss now is what I will do next is discuss a very particular simple architecture for discriminators and estimators, which is a linear architecture. So we imagine that we have some observations P of Ri, this is a vector given some parameter, and we want to study how to set up optimally a linear discriminator and estimator. So a linear discriminator will have the form theta of sum wi ri plus b. This is the Heaviside function, so this is either 0 or maybe we could also write here sine of this thing to be more consistent with what we did in the context of supervised learning. So this will be plus or minus 1. And we want to ask how to set up the weights such that we do as best as possible, and what can we say about a linear discriminator. And a linear estimator is even more simple. It will be just theta hat equal to sum over I wi ri plus b. So this we will do next week. Maybe Neta will start talking. We'll talk a little bit about. I don't remember if she will do it today or next week about linear, some aspect of this already today. Okay. So see you on Thursday.
I left mine at home and I need it for to keep the regular marking. So thank you.
כאילו אי אפשר לראות את זה ישירות בעיקר בגלל המינוס אחד הזה שהוא קצת אנגלי, אבל ברמת העיקרון מה שאת עושה כל פעם שאת צריכה להוכיח משהו בסגנון הזה, אז לקחת את המטריצה שלך, הופכת אותה לחילוף טטרלי, ובעצם לכתוב את טכנית כותבת את ה-U טרנספוז יותר דפניתיות. בגלל שזה מטריצה חלק פוליטי, בגלל שזה כאילו מטריצה חיובית, אז כל הערכים הפנימיים שלה חיוביים. כאילו אני אומר את הקביעה של ההוכחה, אני לא יודע לקחת את זה. ואז מינוס אחד של המטריצה הזאת זה סתם אומר לעשות מינוס אחד על אחד חלקי הערכים העצמיים, ומשם כאילו משהו כזה עומד לצאת, אבל אני לא, כאילו זה ממש תנאי שקשור רק צריכים לצייר את זה.
אם יש לך סיכום מההתחלה לא תעשי
כאילו, לקבל אינטואיציה על מטריצה,
על מה דיברת?
חוץ מממש לרשום כאילו זה יש, אם המטריצה היא לא אלכסונית ויכול להיות שיש בו עוד ערכים, אז זה תמיד כאילו זה כאילו זה כבר תלוי בשאר הערכים, זה רק יכול עקרונית להכפיל אותו, אבל להציג נורא קשה להכפיל
ו-D זה המימד?
זה יכול רק להקטין את זה, אבל כאילו להגדיל את זה. בגלל שחיובי,
שכאילו מה
אנחנו
שאנחנו
יודעים
חושבים
שאפשר
שהוא
לעשות
קבוע
ככה.
בכל סכום, זה עושה מקסימום אלפיים אלף.
וכל הערכים הטבעיים פה,
תזכיר אותו בשני טורים, אבל בשביל אותו רוב. זה לא אחרת אפשר...
שבגלל שחיובי של הערכים הטבעיים של הכל
כאילו זה לא
חיובי,
שומר על המספר
אז אם אני יכול לקחת כן, וגם את הגל הזה צריך חיובי, נראה ככה, ואז J
וכאילו
אחד
ואז תמיד
אלפא
אני אפנה לו, כאילו בקבוצה שהוא אמר לו,
וקטור
שמשכו
אלפא,
למטה.
אם אתה
כאילו,
כאילו במקום, אתה כאילו כן יכול לשנות את
אתה
זה,
צריך
זאת אומרת,
איכשהו
אתה כן
לזמן
יודע
וקטור
לתג'יר,
בכל מקרה,
כאילו שמת
זה
כל
יהיה
ככה שתמיד המספר של
U
העברות
וקטור
כאילו זה
אלפא,
הקונספט שלך, לא המקסימום
כפול
פיינרייט, אלא סך הכל פיינרייט, כל
מי
הרשת,
אלפא,
אז כאילו אומר שזה עדיף, תמיד עדיף לאט, לא משנה במה, אבל כאילו,
אחד חלקי
רק אמר את זה, לא...
U אלפא, משהו כזה, זה יהיה
הוא עשה
כאילו,
לנו
זה יהיה
ספוילר
זה.
לשבוע.
טוב, צריכים לראות, מה זה הדבר הזה, כאילו. זאת הדרך קל לחשוב את הדבר הזה. כן. וזה פשוט U
ואז זה כאילו,
J אלפא אלפא מינוס אחד, אחד חלקי אלפא מינוס הדבר הזה,
תודה.
U אלפא
אולי אני אדלג.
למדה אלפא טוב. נכון?
מה, הפגישה הייתה ארוכה?
אני בורח באמצע, הבעיה היא שפעם, כאילו, גם הגעתי יותר מאוחר, וגם כאילו, לא יודע,
משהו ארוך. התחיל ב10 לפנות עכשיו.
זה תמיד לוקח, תמיד ארוך. כאילו, יש איזה ציון אותם מה הוא חשב על מה שלחתי, לא הספקתי. לא, הוא אמר שהוא ראה את זה כשאנחנו לדבר.
זה אומר שיש לו מה להגיד.
טוב, אם יש לו מה להגיד.
נשמע כאילו פשוט אלא אם כן טעיתי פה
יש לו
באחד
כמה
החישובים,
שדומה
שניהם נראים כמו אחד